Okay, cool. So let's begin. So we are in lecture 14 now, and today the main agenda is going to be to give you one algorithm for univariate polynomial factorization. Um, uh, there is another algorithm which is also really nice, but I'm not sure at this point if I want to do that as well, or maybe just point you to some reading material for that. And it's also not clear if I will be able to complete this entire agenda. But here is roughly speaking what we are going to do. We're basically going to try and move towards a complete algorithm for polynomial factorization. And this will sort of go through sort of three major steps. There will be two corner cases that we will deal with. And those will be with respect to, when you have repeated factors or when you have two irreducible factors that have different degrees. So normally many of these factorization algorithms, they basically try to exploit some form of asymmetry. Like if your factors are somehow different in some sense, then the ways in which you exploit them. So we'll basically see two different sort of special cases where we can easily find a factorization. And then will come the main setup, which is like, once you know that none of these things hold and you are in a very sort of very symmetric sort of setting, then you appeal to what is called the Chinese remainder theorem, and we'll come up with an algorithm that uses the Chinese remainder. Okay, so in some sense, this is the algorithm we are going to see, and in some sense, this is the tool that you're going to learn. Okay, and the tool is, you've probably seen Chinese remainder theorem in other contexts, so it's a super powerful tool to just have in your tool book. Okay, good. So the last couple of classes we've been looking at a whole bunch of stuff with regard to finite fields and various properties about finite fields, etc., etc. And let's just recap a few things that we will need so that we're all on the same page. So finite field, we saw constructions of finite fields. So there is this traditional FP, which is a set of all residue classes modulo some prime P. This is one of your the easier versions of finite fields. But then there are other fields which are of the form you work with FPX and go modulo some irreducible polynomial. By the way, I do want to correct something that I mentioned. I said that monic usually refers to the fact that the leading coefficient is invertible. Since this is something that I'll keep using again and again, I want to restrict myself to the leading coefficient being 1. So in some sense, if the leading coefficient is 2, I am expecting you to just divide by 2 so that the leading coefficient becomes 1 and think of that as the problem. And usually over fields, this doesn't make much of a difference because you can always divide by non-zero things. But it becomes relevant when you're dealing with rings and stuff like that. But so from now on, whenever I refer to monic, I will refer to the fact that the leading coefficient is equal to 1. Okay. So, and this is something that we have been sort of using again and again and again. And I want to sort of make sure that this is something you become very familiar with, which is just the fact that if you look at product of x bar, if you look at the factorization of x bar q bar r minus x over, over some field fq. I think in class I mentioned this being a prime p, but there's nothing special about it being fp as opposed to fq. And usually Q is referred to denote, it's used to denote that Q equals P bar R, where R could possibly be greater than 1. In the sense that Q is just to somehow indicate that you'll be dealing with a finite field. It could either be one of your fields of the type FP, or it could be a field of this type. Okay, and what does this decomposition say? It says that the factorization of this is basically going to split into all possible monic irreducible polynomials of the right degree. What is the right degree? Well, the degree should divide R. So for instance, if Q was equal to 6, if R was equal to 6, then you're dealing with the product of all polynomials of monic irreducible polynomials of degree 1, 2, 3, and 6, because those are the divisors of 6. Okay. And this is a super useful fact, which we have already seen a few applications of, and today we will see more applications of. Okay. And last time we saw one algorithm which was this irreducibility testing algorithm, which is you're given a polynomial f, which is a univariate polynomial, and you want to know, is it irreducible or not? Okay. And we basically just use the above property that we have written down. We know for a fact that if there was some irreducible factor, well, for the right R, it should show up on the right hand side. Okay, so if f is not irreducible, it must have one of those irreducible factors must have degree at most d by 2. So let's just do a GCD of f with all possible x bar q bar r minus x, where r ranges from 1, 2 all the way to d by 2. So if there was an irreducible factor, you will catch it. Okay, so then in that case, you will say, no, it's false. I mean, like, it turns out we did find an irreducible factor. But in other cases, you know for a fact, I mean, like, if it so happens that you didn't find this at all, then it basically means that there are no irreducible factors of degree at most d by 2, which means the polynomial itself must have been irreducible to begin. So this is basically fine, except that this, you can't do that traditional GCD algorithm because the degree of this polynomial is huge. So one needs to be a little clever about it. And the idea is that whenever you want to compute the GCD of f with whatever, q bar r minus x, I don't know why this color is alone black. Okay. So you just use the fact that GCD of f and g is the same as GCD of g mod f and f. This is just one step of the Euclidean algorithm. And the modulo is something that you can split across sum, and so you have this. So the task basically boils down to, can you compute this quickly? Okay. Currently, this is a huge degree polynomial. It has degree q bar r, and r could be as large as n or d or whatever. Right. So you can't just do the traditional division and remainder operation. But nevertheless, you can compute in general this thing called, I don't know, the GCD of a power of a polynomial, which is whenever you want to compute the GCD of g bar k with f. Turns out you can actually compute it in log k and degree of f, degree of g in log k. Okay. And this is something that is there in your problem set 2, which was, I think I put it up maybe on Sunday or something. So this is something that you are explicitly asked to just code up and just convince yourself that that's what you do. And yeah. So once you do this, you just instantiate it for g equal to x and k equal to q power r. And you come up in, this basically completes the irreducibility test. So there's a polynomial time algorithm to tell you whether or not a certain polynomial is irreducible over the base. Okay, so this is basically what we saw last time. So maybe let me just pause here and ask if there are any questions, if there is something that you need clarifying before we proceed to the content of today's lecture. Okay, good. So I hope things are therefore okay, and let's proceed with today's lecture. So basically, before I go into the full thing, let me just give you a roadmap of what we are going to do. Okay, so the standard problem of factorization is I give you a polynomial f and I ask you to compute its factorization into irreducible factors. We already mentioned earlier that such a factorization is unique because univariate polynomials form what is called a unique factorization domain. And so there is a unique answer that I'm expecting. But let's simplify the problem a little bit and let's just ask the following. Tell me, either you tell me that the polynomial is irreducible, in which case that is the factorization. Otherwise, I'm only going to expect you to find a non-trivial factor. Okay, so that's going to be the, okay, let me just turn off this join sound. Okay, so that's going to be the ask. Okay, I basically want to say either show that it is irreducible or find one non-trivial factor. That's it. Okay, and the way we are going to do this is by the following sort of a few special cases. So there will be two different special cases we will consider. We will solve those two cases first because they're actually quite easy. And then will come the main task, which is, okay, if none of these special cases work, what do you do? Okay, so the first special case is if it so happens that f has a repeated factor. By that, what I mean is there is some polynomial g, I mean, which is obviously not like a constant, such that g squared happens to divide f. So in some sense, it's like, no, there is a factor with multiplicity. right? If you understand. Okay. So now in that case, what I want to find some non-trivial factorization. Okay, and we'll first ask ourselves, is this something we can do? The next thing we are going to do is, like, once we manage to do this, we will just assume without loss of generality that the hard case is really when f happens to be square free in some sense, in the sense that it's a product of irreducible polynomials, all of which are distinct. Like, there are no repetitions, because if there were repetitions, you would have found a factor using step 1. So the only reason at this point, you can just assume that you are in a setup where the polynomial happens to be square free. So the next task is going to be, suppose it turns out that among the factorization that f has, there are factors of slightly different degrees. Like, there's one which is of degree 7, the other of degree 10 or something. Okay, there are two factors of different degrees. Okay, in that case, can you find a non-trivial factor? Okay. So in that case, we'll figure out how to do this. And at this point, once we solve subcase 2, we will be in a situation where you are told that f is a polynomial that is broken up into irreducible factors, all of which have the same. And you also know exactly what that degree is. So as we'll see from the algorithm, we will know exactly what that degree also is. And then we would want to know, can we find a non-trivial factor? And this is the main subcase that we will try to solve. So technically speaking, you don't need to do 2 in order, you can directly come here, but I think doing 2 is instructive. Okay, so I'm going to nevertheless do this special case and then finally get to this task. So this is going to be the rough roadmap of what we are going to do. Okay, so let's proceed with the first part. Suppose I promise to you that there is some non-trivial g such that g squared divides f. And I want you to find a factor of f. So any thoughts? So again, like, it's always useful to go back to things that you have come across when it comes to repeated factors, etc. Yeah, go ahead.
Why not we go do the quotient and look for that is not filled in case? That's also a way, right?
I mean, you want to just take the quotient of fx over. So I guess what Saurabh is suggesting is that let's just look at the following: fx quotiented with f of x. Okay.
Yeah.
Okay. So then what?
If it is irreducible, then we will have a field, right?
Yeah. But we already know it is not irreducible, right? Yes. I mean, because if it was irreducible, we would have said irreducible.
Yeah. So that means there is an element which doesn't have any inverse or something like that.
Yeah. But how do you find such an element? That's the problem. In fact,
yeah. So I think that g square will somehow we can manipulate to make it element in fx. If you see the g in fx by small fx.
So here is a general principle to keep in mind. Okay.
Yes.
It's always good to think about what happens in the integer setting. Suppose I give you an integer n. Okay. If it is prime, then whatever z mod n is a field. Great. Okay. We haven't seen a primality test, but we will see that in the course. But let's say we can figure out whether it's a prime or not.
So now, g is known to us, right?
No, g is not known to us. That's the whole point. All I tell you is that there is some g such that g squared divides f. I don't know what g is. Okay, so it's a little tricky because the thing is, I mean, like, it's not easy to find something that is not invertible in a certain domain. Because in some sense, if we could do that quickly, we would be able to factorize integers very quickly.
Yes.
And we don't expect to do that very well. So therefore, there's something about polynomials that will become very crucial. Something that we can do to polynomials, which we don't know how to do to integers.
Repeated root you have said, right? So we
yes. So basically,
we'll look for f.
Sorry, look for what?
F dash.
Okay, what is f dash? I mean, like,
derivative of f.
Good, excellent. So that's the word I was looking for. So the question is, what about derivatives? Okay. And hopefully, I mean, like this becomes a very natural thing that you will try out whenever you're talking about repeated root and stuff like that, because somehow derivative seems like the right thing to look at. Okay. But one needs to be a little precise about things. Like, what is a derivative? Normally, we would say f prime of x is equal to the following, which is limit of epsilon tends to 0, f of x plus epsilon minus f of x over epsilon. This is the standard definition of what a derivative is. Okay, except we are working over a finite field and we don't have the luxury of things like epsilon going to 0 and so on. So in some sense, the right hand side doesn't seem to make sense. Okay, but I mean, mentally, it feels like, I mean, we sort of roughly know what derivatives are supposed to do. Okay, and we're not dealing with things like sin x or cos x or something. We are dealing with polynomials. And for polynomials, we know precisely what a derivative is supposed to do. Okay, so let's define a notion of what is called a formal derivative. I mean, it's like we are basically trying to borrow intuition from the standard derivative, but we are just setting up the algebra in a way that it makes sense over the world we are working in. That's it. And okay, so here is what I'm going to do. I'm going to just define a map. This is like an operator D, which takes as input a polynomial and spits out another polynomial. Because that's what derivatives are supposed to do. It takes a polynomial, returns another polynomial, and it behaves in a linear fashion. That is, derivative of f plus g is the derivative of f plus derivative of g, etc. etc. Okay, so let me just do the stupidest thing that I can do. I will just tell you the derivative of 1 equals 0, because that's what I'm used to. Okay, and the derivative of any monomial x power m, we will just define it to be the familiar mx power m minus 1. Okay, and now you basically say extend linear. Okay, that is now whenever you have things that are made up of sums of such monomials, because it's a linear operator, you know precisely what it's supposed to be. You're literally doing the algebra that you would do when computing a derivative. And I'm just defining that as a linear operator. And I'm hoping that it has all the necessary properties that I want from a derivative, because I have some mental intuition of what derivatives are supposed to do. And we are somehow hoping that that continues to remain. Okay, so something that is actually easy to verify, and I'll really, I mean, like you to try it out, which is that it satisfies the product rule. Okay, that is, whenever I give you two polynomials f and g, and I ask what is the derivative of fg, this is actually going to be equal to f times the derivative of g plus g times the derivative of f.
Leibniz rule.
Yeah, it's just take this. I mean, take this definition. I mean, of course, you probably seen this when this was the definition, and you just need to convince yourself that the same thing holds even when this is a definition. Here, of course, I'm only restricting myself to polynomials because I have no idea how to take derivatives of other random things. Okay, but nevertheless, as long as you restrict yourself to polynomials, this equality holds. This is just a standard derivative rule. And something particularly useful for us is that the derivative of g squared, it's going to be 2g times derivative of g. I mean, it's just a special case of what happens here because it's like g derivative g, g derivative g. So you get 2g derivatives. Okay. Okay, great. So why was the derivative useful? So Saurabh, would you want to elaborate on why you thought derivatives might be useful? So what would happen if you take a derivative of f?
So that will divide by g only, right?
That's right. So whenever there is a repeated factor, I mean, in some sense, if you have a root with large multiplicity, then you know that is also a root of the derivative. The analogous statement is if g squared divides f, then actually g should divide the derivative. In fact, something far stronger is true, which is that if g cubed divides f, then g squared will divide the derivative. And similarly, g power k, if it divides f, then g power k minus 1 will definitely divide the derivative. Okay. Okay. So and this is a very simple proof, which is to just show that what is the derivative of f? The derivative of f is, okay, let's say f is equal to some g squared times h. Okay, then the derivative of f is equal to
2g dg
derivative of g squared times h plus g squared times derivative of h, which we now know that this is 2g derivative of g times h plus, oh sorry, this should have been h, g squared times derivative of h. And clearly g divides the right answer. Okay, and of course, I mean, like the same thing, had I replaced 2 with a larger number, let's say 7 or something, then you will see that g power 6 divides the right answer. Okay, there's nothing fancy going on here. Okay, this naturally leads to the following extremely simple algorithm to find a factor if it so happens that some g squared divides it. I don't need to know what g is at all. Okay, which is just the following. Let's just compute the derivative. I'm given f as a coefficient of f as a bunch of coefficients. So I know precisely how to compute the derivative I'm interested in. And then let's just take the GCD of f prime with f. Okay, we know for a fact that if there was some g such that g squared divides f, then note that g is something that divides both f and f prime. And therefore it will show up in the GCD. Okay, and is there an issue with this algorithm? Can someone point?
I forgot. So the GCD algorithm is also polynomial type.
Sorry, let me just answer Saurav's question and I'll come back to you, Shantanu. So the GCD algorithm is something that's going to run in polynomial time in the 2 degrees involved. So if f and f prime have degree d, say, then the GCD algorithm is going to take roughly poly d time.
Means nearly to d, means if
yeah, it's almost linear. It's almost linear, but at this point, like, we are okay with any poly d is fine with this. Okay. Shantanu, you had some question?
Yeah. GCD will have much more than g. It can have any other factor also.
But that's okay, right? I mean, like, as long as I can convince myself that it's a non-trivial factor, I'm fine with it. As long as you don't tell me that the GCD is equal to f itself, then I'm not making progress. But I would like to say that the GCD is not equal to f because f prime has degree 1 less than what f is. So therefore, I can't get f. I mean, am I saying something correct, or has someone caught me on a mistake?
Like, so we are saying, actually, I mean, g square, like g should not divide h or some.
No, but it doesn't matter, right? I mean, like, all I'm saying is the following. G is something that divides f prime and it also divides f. And f prime is currently a polynomial of degree d minus 1 if f happens to be a polynomial of degree d. Right? So when I take a GCD of a polynomial of degree d minus 1 and another polynomial of degree d, I will end up getting something of polynomial of degree d minus 1 or less. So it's guaranteed to be some non-trivial factor once you promise to me that at least g divides. So it will be non-trivial, unless something really stupid happens. So it's not quite, this algorithm is not quite done. So there is a subtle issue with this.
You will get the GCD of f prime and f. You will get some g dash, not g.
No, why not? So currently, I mean,
because I'm saying to that it might happen that there are 2 g1 g2 such that g1 square divides f, and
that's totally fine as long as you tell me this is something that is strictly smaller than f in degree. We are making progress. All I wanted was to get some factor, right? I mean, like, yeah, if there are multiple repeated factors and I get g1, g2, g3, I don't particularly care, as long as you don't just return f directly. Because if the GCD is equal to f, then I'm not making progress at all. So what can go wrong here? So, okay, so here is where I said something which is actually false. I claim because f prime has degree 1 less than f, like at least 1 less than f, I am saying this GCD must be non-trivial. Like the GCD cannot be F. Why is that true?
No, the GCD has to divide F, right?
GCD has to divide F.
And
F
F
prime.
It
prime.
also has to
And
divide F prime.
so is it possible that a degree D polynomial divides a potentially degree D minus 1 polynomial? There is only one case in which that can happen, which is if this polynomial happens to be 0.
0 degree polynomial, yeah.
Okay. Now, this is something that will usually not happen when you are dealing with real numbers and real polynomials at all. But finite fields behave in strange ways. Like for instance, suppose your polynomial f was x power p plus 2x power p squared. What would the derivative of this be? So this is going to be px power p minus 1 plus 2p squared x power p squared minus 1. But you're working over a field, say fp, and this stupid thing is 0 and this stupid thing is 0. So therefore, this entire thing is going to be equal to 0. Okay, so there are these strange artifacts that you end up with. This is something that you will never deal with when you're working over rationals or reals or something. But finite fields have this annoying characteristic problem. Okay, which is that things that you don't expect to become 0 might become 0. So we need to be a little bit more careful. So we should ask ourselves, what if d of f becomes 0? In which case, this algorithm is not going to do anything. It's going to basically return f. Okay, so let's ask ourselves, when will d of f be equal to 0? In fact, the above thing exactly tells you when that might happen. What sort of polynomials will satisfy that f prime of x equals 0?
The previous example, you worked in ZP.
Yeah. So I'm thinking of, we are dealing with FP here, and I just gave you one example. Like this could be something like, I don't know, let's say 7p or something, in which case this will become, okay, my colors are all weird, 14p x power 7p minus 1. So therefore, everything on the right hand side is 0 because over fp, p equals 0. Okay. So the only way df can be 0 is if the derivative of every monomial involved suddenly becomes 0. Like f had these monomials of the form x power n. But every time I took a derivative, the damn thing became 0. So when can that happen? It must be the case that p divides n. Okay. So the only way your polynomial can be 0 is if it so happens that every monomial that you have in your polynomial, its exponent is somehow divisible by p. Okay. So to write this differently, so d of f is equal to 0 if and only if every monomial has an exponent which is divisible by p. Okay. Which means I just want to just write this and then tell me if this doesn't make sense. X power p for some f tilde. Okay, that is what I mean is if I have a polynomial of this form, my f tilde is going to just be x plus 2x power 7. And all I have done is in this polynomial, I just replaced x with x power p. So that I get x power p and 2x power 7. It's just a slightly different way of saying I want to divide by p in the exponents everywhere. So I am doing that in the process of rewriting my polynomial as f tilde evaluated at x power p. Is this okay so far? Okay, cool. So now notice over fp, f tilde of x power p is the same thing as f tilde of x, the whole power p. This is again one of these weird quirks of fp. Because if you, x plus y the whole power p in fp, it turns out to become x power p plus y power p. Because all the binomial coefficients in the middle will all become 0. Okay, so this is because of things of the form x plus y the whole power p equals x power p plus y power p.
Sir,
Yeah, go ahead.
I'm a bit confused actually.
Okay.
Is the implication is too much, isn't it?
Which implication?
The df equals to 0 equals means all the exponent of x to the power p will be.
No, because it has to be, right? Like suppose, let's say f has one monomial whose exponent was not divisible by p. Then in the derivative of f, the derivative of that monomial will show up.
Can you give an example?
So for example, so suppose, let's say you're working with, let's say p is equal to 5.
Yes.
Okay. And suppose you're working with some polynomial that has x cubed plus a whole bunch of stuff.
Yes.
That is, none of this is x cubed. I mean, like it's like a whole bunch of other things. So when I take a derivative of this under the derivative operation, this would have become 3x squared. And I know for a fact that 3 is something that is non-zero in my field.
Yes.
So this term is going to survive in D of f.
But the definition that you have given, we are putting in the place of x cube, we are putting x to the power 5, right?
No. Why are we putting? No. I'm saying there are two separate implications that we are making. The first implication we are making is that the only way D of f can be 0 is if f is a polynomial such that every occurrence of x or every monomial has degree that is divisible by the prime p, where p is the characteristic. Is that okay?
Yeah, that's.
So that means my f cannot be of this type at all, because x power 3 is just not allowed.
Okay.
So the only sort of polynomials that may be something that becomes 0 is something that looks like x power 5 into 3 plus 7 x power 5 into 2, etc., etc. And I'm just basically ignoring these 5s and calling that my f tilde.
Okay.
That's what I'm doing. So that's what this thing is. And it so happens that because of the way fp works, is that f tilde of x power p actually equals f tilde of x, the whole power.
Okay. Thank you.
Okay. So this basically suggests that I've already found a factor, which is f tilde. So yeah, so you just need to modify the above algorithm to basically say, let's compute the derivative. If this derivative becomes 0, then just compute f tilde and return f tilde. If the derivative is non-zero, then you do the GCD computation. That's the modification that you do. Okay, so it's again one of these weird quirks of finite fields that things might become 0, but fortunately things become 0 in a very predictable way. Like when it becomes 0 for a stupid reason, and normally those stupid reasons are something we can explain. Okay, cool. So if this is okay, so now let's go to the next thing, which is how do you handle the situation where you now have irreducibles of different degrees? Okay.
Hey, sorry.
Yeah. Go ahead.
Got lost for a second. So here once. So suppose in the case when df is 0, then we were going to find. Then we were going to do what? Find the.
You just find f tilde. That is right. Look at the coefficient of f. You will readily see that the only monomials that are present, the only non-zero coefficients, correspond to exponents that look like x power, I don't know, kp for some k.
Right.
Just define f tilde to be whatever summation alpha kp f power k or something. Sorry, x power k. That is just drop off that p is in the exponent. That's your polynomial f tilde, and return f tilde of x as a factor. Its degree is actually going to be at least like 1 by p of whatever the degree of f was. So it's certainly a non-trivial factor, and you have found something you could return.
Right.
Yeah. Okay. So this is what you would do in the setup of repeated factors. So it's basically the traditional GCD algorithm. Sorry, the derivative-based approach, except this annoying corner case of the derivative becoming 0. Okay. Good. So the next thing we are going to do is handle the situation where you have you're working with a polynomial and some of its irreducible factors have different degrees. Okay, so here is the setup. Okay, let's say f looks like g1 through gk, and we may assume with a lossy generality that f is square free, in the sense that none of these gi's are basically the same thing. They're all distinct gi's. And let's say d was equal to the degree of f. Okay, now among these gi's, some of them have degree 1, potentially. Maybe none of them have degree 1. Some of them may have degree 2. Some of them may have degree 3, etc., etc. Some of them may have degree D, but mentally we know that that can't happen, because if any of them had degree D, then it means f itself is irreducible. So f must be equal to just g1 in some sense. So nevertheless, we can just write down this thing where you basically say, let's group all degree 1 terms and put that in g1, in d1. Let's group all degree 2 terms, put that in d2, etc., etc. Okay, where basically di refers to the product of all those gi's whose degree happens to be equal to 1. Okay. Now, if someone tells us that there are irreducibles of different degrees, then what that means is that 2 different di's are actually non-zero. Sorry, non-trivial. They're not 1. Because one of those, no, there is a gi of a certain degree, which means it will go into one of these buckets. And there was a different gi of a different degree, which means it will go into the other one. Right? So that's the setup that you are. Then currently my goal is to find all of these di separately. We'll then deal with the issue of splitting them up into its factors. But at the moment, I want to split up the factors of G into, these are the product of all degree 1 factors, then degree 2 factors, degree 3 factors, etc., etc. Okay. And this entire task is referred to as distinct degree factorization. If I can spell correctly. Okay. So let's ask ourselves, can we compute d1 through dd efficiently? Okay. Now, here is the first question. What is d1?
D1 is it's just a product of linear factors.
It's a product of all linear factors that are present in F. Like all factors of the form x minus alpha that happens to be present inside F. So how do you extract just those out?
So the derivative is non-zero at those points.
At this point, you may assume that the derivative is non-zero, etc., because those are cases that we have handled already.
F of alpha will be 0.
That's right. But I can't search over all possible alphas because potentially P is a very large prime.
Okay.
So I don't have, I want to run in log P time. I don't want to run over all P.
Okay.
But yeah, but you're on the right track in the sense that, you know, is there a polynomial that sort of groups together all possible linear factors in one shot?
Oh, that's x, whatever, x to the p minus x.
That's right. So what do I need to do? So x bar p minus x is a product of all possible x minus alphas, some of which may be factors of f, some of which may not be factors of f. But it just has everything together. Okay, but if you want to extract out only those that happen to be factors of f, what do you do?
Take GCD with.
That's right. So you just do GCD of x power p minus x with f. And this will basically extract out all possible linear factors that f has. Okay, it's a good thing that we have already gotten rid of repeated factors, because if x minus alpha the whole squared were to divide f, then only x minus alpha will show up in the GCD. Right? I mean, one of them will be lost somehow, but that we have handled that, you know, it's square free stuff like that, so we don't need to worry. So excellent. So now what is D2?
Product of all degree 2 irreducible.
That's right. So what should that be? I mean, like, So the most natural thing seems to be to look at GCD of x power p squared minus x over f. But do I need to massage it to make it correct at this point? So what will this GCD end up giving us?
No, this will have even irreducible of degree 1. I mean,
that's right. Okay, so you first compute this and just divide by d1. Because this will include both irreducibles of degree 2 and 1. Okay, fine. So therefore, let's get rid of the degree 1 part because we have already computed. Okay, and in general, what you would do is you will basically compute this GCD, which is, oh, I kept using P everywhere, which probably should have been Q, whatever. I mean, you don't understand what I mean by that. So you basically, if you want the ith degree I irreducible factors, what you will do is you will first compute this. But this will involve not just the ith degree factors, but it will involve all other DJs where J divides it. So just divide off by all those other things. I mean, things that you have already computed, you can divide them off. Okay, and once again, all these GCDs you do via repeated squaring because the degrees are way too large. Okay, so you use the same repeated squaring algorithm that we had described earlier and use that to compute this particular GCD. And so this basically tells us that you can do distinct degree factorization. And if you're promised that these are irreducibles of different degrees, two different DIs will be non-trivial. Right? So you can return one of those DIs as a non-trivial factor. Okay, so that actually handles the situation where somebody provides us a polynomial with a promise that, by the way, I know for a fact there are two different degrees, get me a factor. We just compute all of D1, D2 all the way till some D, whatever, DD or something. And if we find two different chunks which appear to be non-trivial, we just return one of the chunks and say, hey, I've just found an irreducible factor. Sorry, not irreducible, I found some factor. Okay, so that solves the distinct degree case. Are there any questions so far? I mean,
so right now the only case left is when your given polynomial is a product of irreducible, like square-free product of irreducible polynomials of the same degree.
Right, and you also know what the degree is, because if you did the distinct degree factorization, you will basically notice that one of those DIs happens to be equal to f itself, and everything else was equal to 1, which basically means f is broken up into irreducible factors all of degree I. Okay, I'm just using, I seem to have used R from this point onwards. So this is the setup. You are given a polynomial, you are guaranteed it is square free. You are guaranteed that every irreducible factor of f happens to have degree R. And this R is something that you know. Okay, and the goal is to find a non-trivial factor of f. Okay, so it turns out there are two different algorithms for this. One is called the Cantor-Zassenhaus algorithm, which is a randomized algorithm that runs in n and log q time, where n refers to the degree of f. Okay, so it's great in the sense that the running time is sort of the sort of running times that we are looking for. Okay, so it's a fantastic algorithm, except it's randomized. So in that sense, it's a little unsatisfactory. On the other hand, there is a different algorithm by Berlekamp that gives a deterministic algorithm which is suitable for large fields over small characters. So the running time is n and log q and p, where q looks like p power r and p is the prime. So the second algorithm is very useful if you're working over a field that looks like f2 power 10,000 or something. Okay, but it's not useful if your field itself is over a very, very large prime, because then it's an algorithm that runs in time n comma p, which is perhaps not what you want. Okay, so I do want to point out that this Cantor is David Cantor, because this is an algorithm from the 80s, as in it's the 1980s, and it can't have been George Cantor, Okay. So this is an algorithm by David Cantor and Hans-Zassenhaus. And Berlecamp's algorithm is actually from the 60s. It's much old, much earlier than Cantor-Zassenhaus. Okay. And turns out a major open problem is to do this in deterministic time n and log q. And we still don't know how to do this. There are various other subcases that we know how to solve. That again use something about the asymmetry of roots and so on. But the general thing of trying to solve this problem in deterministic time n and log q continues to remain open. Okay, so what we are going to do today in the rest of the time that we have is to look at the Cantor-Zassenhaus algorithm, where I might make certain assumptions and just try to convince you that somehow get you to buy these assumptions, because hopefully they will be reasonable. And we'll either prove it prove those claims in today's lecture, or maybe we might push it to the next lecture. Okay, so that is going to be what we are going to do here. And it actually comes back to what Saurav had mentioned earlier, which is to just try and understand what does this quotient ring look like. Okay, I know for a fact that if f had been irreducible, then this quotient ring should have been a field. Okay, fine, f is not irreducible, so it's not a field. But is there some structure? Okay, and that's what we're going to focus on. And we're going to try and understand what is the possible structure that this object, this fx quotiented with small fx, looks like, and try and somehow build an algorithm keeping this particular structure. Okay, so if f equals g1 through gr, we know for a fact that this is not a field. Okay, can someone give me an example of a specific point which is non-zero but not invertible? I mean, in this case, I've actually told you that a factorization of f. I've told you that f equals g1 through gr. Can you give me an example of a non-zero element that has no inverse? I don't know if Saurav is saying something, I'm not able to hear it.
No, I'm not.
Oh, okay. So I suddenly saw the mic show up. Okay. What are things that are zero here? It basically means things that are divisible by f. Okay. So can you come up with a polynomial that is actually not divisible by f, but I can multiply it with something else so that it becomes divisible by f? So such a thing is called a zero divisor.
So if we just take
G1 plus f.
Yeah, so right, G1. I claim G1 cannot have an inverse. Why is that? Because I know for a fact that G1 times G2 to GR, this is equal to 0 in this world. Okay. Well, if this guy had an inverse, then I can multiply by that inverse and get rid of something like this. It will tell me that G2 to GR equals 0. But we know for a fact that's not true, because this is a polynomial of smaller d. Right? So therefore, the very fact that G1 is a zero divisor, in the sense that it's non-zero, but there is a way to multiply it with something else to make it zero. Okay? Such a zero divisor cannot have inverses. Okay? And in fact, almost all factorization algorithms in some sense is basically a hunt for a zero divisor. I want some concrete way to prove that this damn thing is not a field. And I want to do that by somehow constructing a zero divisor. And if I can do that efficiently, I will find a factor. Okay. So I want to know, okay, fine. I know that therefore this is not a field because there are things like this. But nevertheless, I want to know what does that look like. And let's once again step back and take some inspiration from integers and ask ourselves the same question over integers. So for instance, if I start with an integer like 42, which we know is not prime, okay, what does this field look like? Sorry, not a field. What does this weird object look like? Okay, these are all residue classes when you go modulo 42. Okay, and I'm guessing that you have seen the Chinese remainder theorem in some other course or something. Nevertheless, we will see that. Now, turns out that going modulo 42, rather than telling you what is the remainder modulo 42, I can instead tell you what is the remainder modulo 2, modulo 3, and modulo 7. It seems like that has all the information you need in order to figure out what number I'm looking at. Okay. At this point, this feels, I mean, like I've just written some symbols here. It might feel a little unclear what the thing is, but just think of the right-hand side as consisting of a 3 tuple of elements where the first coordinate comes from this, second coordinate comes from this, and the third coordinate comes from this. Okay, so there are 2 elements here, there are 3 elements here, and there are 7 elements here, and 2 into 3 into 7 equals 42. So at least there are as many elements on the right-hand side as the left-hand side. But something stronger is true, which is every element here has a unique representation here, and every element on the right-hand side has a unique representation on the left-hand side. And basically, it doesn't matter which perspective you take. You are still talking about the same thing. If you want to add 2 elements on the right-hand side, you add them coordinate-wise. If you want to multiply 2 elements on the right-hand side, you multiply them coordinate-wise. So you would have seen the Chinese remainder theorem to sort of say, given specific residues modulo 2, 3, and 7, there is a unique residue modulo 42 that corresponds to this. That's probably the statement that you have seen, but it's a more general statement about how rings behave. Now, turns out the same thing is true for polynomials too. Okay, and this is in general called the Chinese remainder theorem for polynomials or over ideals or whatever. And this is something that we will see. But for now, I'm just going to take this for granted. And we will see the proof of it either towards the end of today's lecture or we'll push over to the next lecture. Okay, so here is what it happens, that this was the object that you were trying to study, which is that fx quotiented by small fx. And this breaks up into a product of primes, where here primes are these irreducible things. And turns out the ring breaks up into these sort of sub-quotients and something. Okay. But the thing to note is that I don't know what G1, G2 to GR are. By the way, was it GR or GK? I don't know what I probably keep mixing up. Anyway, whatever. Okay. So I don't know what this factorization is, which means the right-hand side is a structure I don't have a handle on. I don't precisely know what, the specific representation, but I know there exists one. It's like this is a hidden basis in this world I don't have access to directly. Okay, so is the statement sort of clear? At least, is it roughly making sense? I mean, this is unjustified as to why these two are the same, but just bear with it. Hopefully, you at least, in your gut, it feels like this is true. And we will formalize it later on. Okay, and we're just going to use this setup and complete the Cantor-Zassenhaus algorithm first. And then we'll come back to justifying why this Chinese remainder theorem works. Okay. Okay, now that we believe it.
GIs are irreducibles, right?
Yeah, I was told F is an irreducible. F is a product of distinct irreducibles. Okay, there are no repeated factors. So in some sense, the irreducibles are all co-prime. Like they don't have any GCD between them. Just like in Chinese remainder theorem, if it was instead of 42, if it was 84, which basically means it's 4 into 2 into 7, then I should have replaced 2 squared here instead. So in general, I mean, we're dealing with the case when all the GIs are distinct and irreducible. So now I have some structure of this type. What is this? What can I say about just this component alone? What is fx quotiented by G1?
Field.
The field.
Right. So if G1, let's assume that all of them had degree K. I think at some point I seem to have switched from K to R or something. But let's assume that all GIs have degree K. Then this is just the field F due to the K. So in some sense, So each component by itself is basically a field. So the right hand side almost looks like one of these vector spaces type things, right? It's made up of R coordinates, where each coordinate comes from this field. Okay, where you add and multiply stuff component wise. It's a weird world that you live in. Okay, and it's just that I don't know what this is. All I know is that there is a representation of this is my familiar world. This is what I have access to. But Chinese remainder theorem tells me that there is an equivalent representation in terms of the product of fields. Okay, so which means if I am interested in a particular polynomial that is present here, there is some equivalent representation of the form alpha 1 through alpha k, where each alpha I belongs to this field fq to the k. Again, I want to stress, I don't know what these alpha i's are. Once I pick a certain edge, I know there exists one, but I have no idea of what these are. Okay, so just to get comfortable with it, the 0 on the left hand side corresponds to the element which is 0, 0, 0, blah, 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 blah. Because it must be the whatever additive 0 element on the right hand side. Right? So it corresponds to the tuple that is made up of all zeros, and the 1 element on the left hand side corresponds to the tuple that is made up of all ones. Okay, now here is a question that I want to ask. Suppose I have an element that looks like 0, 7, 2, blah, 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 blah. I don't care what these things are. Okay, now this refers to something. I don't know what this is. H tilde of x. What can I say about H tilde? What does such a representation tell you? Somehow the first coordinate equals 0. What does that mean? When can that happen? So let's again go back to this thing and say, I took some residue on the left hand side, and I told you that it splits into a bunch of residues with mod 2, mod 3, and mod 7. But if the first coordinate is equal to 0, what does that mean?
Not, I mean, you don't have a residue from that part, right?
No, it's not that I don't have a residue from that part. Or other, what does it mean? It doesn't have a residue. Like, for example, can this number be equal to 7? Because 7 mod 2 is not equal to 0.
Yeah.
So I know for a fact the only way this coordinate is equal to 0 is if whatever number I picked up is divisible by 2.
Right.
Right? So once someone tells me that this is the representation it looks like, again, I don't know what G1 is, I don't know any of these things, but I know for a fact that if your representation has some zeros and some non-zeros, what this means is that this is something that is divisible by G1 and is not divisible by G2 or G3, because those two coordinates happen, I'm told that it is not 0. Okay, so this implies that whenever I take the GCD of H tilde with F is guaranteed to be non-trivial. Okay, because I know for a fact that whatever this GCD is, it must involve G1 and it cannot involve G2. So I must get some non-trivial GCD. Okay, again, I don't know what this is. I don't have access to that. But the hunt is going to be to find a particular H tilde with the property that some of its coordinates in this representation, I don't know, happen to be 0 and some of the coordinates happen to be non-zero. Okay, that's what I'm desperately looking for. I want some H tilde that has this property. If I can find such an H tilde, I'll just take the GCD with F and I'm done. I would have found some non-trivial factor. Okay, is this particular?
Are you trying to construct the precise map between F by capital F by small f to
not quite, but I'm going to do something which is, I don't really want to find the exact map. I just want some way of constructing some element with a guarantee that some of the coordinates are 0 and some of the coordinates are not 0. Okay, and maybe once we see the algorithm, things will become a little clearer. Okay,
I mean,
and
so that if we take any element from f by small f, quotients f,
so it will look like some bunch of coordinates here, right? I mean,
yeah, but I'm saying that, yeah, so that alpha I will look like the element that you have picked by modulo GI.
modulo
Right?
the corresponding GI. But again, GI is something I don't have access to. I don't know what GI is.
Okay.
So that's the thing. So the thing is, I don't actually have access to this right-hand side description at all. I mean, this is more like it's only for the argument's sake. Right? Somehow trying to think of what should the algorithm try to do.
So our goal is to find GIs, right? Or something like
Yeah,
that.
eventually that's what we want to do. But I am right now asking for a simpler task, which is, can we find an H tilde such that in the Chinese remainder representation, some of the coordinates are 0 and some of the coordinates are not 0. Did that, I mean, it was,
Yes.
yeah. So this is what we are going for. It's unclear how to do that. But the only thing that I'm telling you at this point is that if you manage to compute such an H tilde quickly, then taking a GCD of H tilde with F will definitely give you a non-trivial factor. So that is why we are doing what we are doing. Okay. So, and this is it's a rather clever algorithm to figure out how to do this. If you have seen the Miller-Rabin primality test in maybe some of your other courses or whatever, then some parts of this algorithm will seem very familiar. Okay, because it's along very, very similar lines. Okay. Okay, good. So, okay, so therefore we know that once we find such an H tilde, I know for a fact that our GCD will be non-trivial. So therefore we want to hunt for some of these H tildes. Okay. Now I'm going to do two setups. There's a part where Q is odd, which to me is the more interesting case. Q is even, one needs to deal with it slightly differently, but it's of a very similar flavor, which I will just mention in passing towards the end. Okay, so suppose Q is odd. Okay, I want to look at the one polynomial that I know, which is x power q power x, x power q power k minus x, which I know splits as a whole bunch of these linear things where all possible alphas that come from this field fq. Okay, now q is odd, so therefore q power k is odd. So let's try and split this in some stupid way. So I know for a fact that it can be written as x into x power q power k minus 1 minus 1. Okay, I've not done anything in particular. And now I know that if q is odd, this thing is even. So this thing looks like something like, I don't know, x power 48 minus 1 or something. Okay. So whenever I see an x power an even number minus 1, there is a natural factorization that you just feel like writing down, right? Which is just x times x power q power k minus 1 by 2 minus 1 and x power q power k minus 1 by 2 plus 1. I'm just doing a squared minus b squared is a minus b into a plus b. Nothing fancy has happened so far. Okay. Okay, fine. So I have one factorization that is already written. And now I have written some factorization that I could do at this point. And let's just compare. So the top looks like x into whatever. I mean, the product of all alpha that is not, alpha not equal to 0 of x minus alpha, right? But I know this factorization and this factorization are the same because they're both factorizations of the same polynomial, right? So, okay, this term and this term matches, which means of the remaining q bar k minus 1 elements, half of them are factors of this guy and half of them are factors of this guy. Right? Because we are both talking about the same factorization. It's a factorization of the same polynomial. Okay, so I'm going to write this as a given name. So I'm going to say alpha is what is called a QR, and this is alpha is what is called a QNR of x minus alpha, where this guy are all factors of this, and this guy are all factors of this. Okay, and QR refers to the notion of what is called a quadratic residue. And QNR is a quadratic non-residue. I mean, you don't need to know what these are, but for people who have seen this before, I'm just writing, I'm just telling you what QR and QNR refer to. But the only takeaway I want you to have at this point is the following, which is besides the zero polynomial, half of your elements of f q bar k minus 0 satisfy this equation, and half of the elements satisfy the other equation. Okay, so that's all I want you to take away. So this is the same thing as saying this is equal to 1, and the same thing as saying this is equal to minus 1. Is this clear so far? I mean, we just basically took the factorization that we knew, split it up, and basically said, oh, okay, so I have this big factor which I know should be equal to this. So half of those terms must have gone here, half of those terms must have gone here. And this is what we have learned at the end of all that. Okay, here comes the beautiful algorithm, which is just the following. Okay, let me just write down the algorithm and then I will tell you, we'll see why this algorithm should work. We will try this a few times. It's a randomized algorithm, so therefore we're going to try a few times and hope to find a factor. Okay, here's what we'll do. We'll pick up a random element h from this object, which is just meaning that pick up a random polynomial of degree smaller than degree of f. Okay, and let's sort of hold our fingers, like cross our fingers, and hope that if it so happens that GCD of h and f is already non-trivial, that is, it's either, it's not equal to 1, it's not equal to f, then okay, great, we have found the GCD, so therefore we're just going to return. This is if we just got unbelievably lucky. Okay, now let's assume that that didn't happen. We didn't really get a GCD. In that case, what we are going to do is compute h power q bar k minus 1 by 2. The mod f. Okay, and then we are just going to return the GCD of h tilde plus 1 with f. And I'm hoping that this test, this entire block succeeds. If it doesn't succeed, I will try out a few times, and I'm hoping that very quickly it will succeed. So is the algorithm clear as to what we are doing? So basically just going to pick up a random polynomial h, okay, and the h tilde we are looking for is basically going to be equal to h bar q bar k minus 1 by 2 plus 1. That is what we are eventually going to hope has the property that some of its coordinates are zeros and some of its coordinates are non-zero. Okay, and I'm therefore hoping that the GCD will return something. Well, if I got unlucky, I'll try this again and again and again. But the point is, I want to claim that I will not have to try this too many times. Okay, so that's the algorithm. This is the factorization algorithm. Okay, so the main claim I want to make is that if it so happens that f is a product of g1 through gr, and you're told that r is at least 2, which is basically saying that you're not in an irreducible setting, so therefore you have at least 2 different factors, and they all happen to have the same degree, they're all irreducible, square free, blah blah blah. Okay, then I want to claim that each such thing will succeed in giving me a proper factor with probability at least half. So if I want to make sure that my error probability is like, I don't know, 1 by 2 power 1000, I'll have to replace this few times by 1000. But that will basically tell me that one of those tries should have succeeded. Okay, so once we prove this claim, the algorithm will be done. Now let's see why that is the case. Okay, what did we do? We started off with picking some h in fx quotiented with f of x, and we picked this at random. Okay, now I know for a fact the world we are working in is basically isomorphic to this world. Okay, so in principle, picking a random element here is the same thing as picking a random element here, except I don't have a handle on the right hand side. I don't know what this right hand side is. Okay, but whatever this h was, it must have some representation of the form alpha 1 through alpha r. Right? And similarly, if h was chosen at random, then the same thing as saying alpha 1 through alpha r was chosen at random, except I don't know what these alpha is. I only know what h is. Okay, so the representation of h is the same thing as alpha 1 through alpha r, but I don't know what the right answer is. Okay, now I want to know what happens when I look at h bar q bar k minus 1 by 2. What is its representation on the right hand side? I mean, this is just Chinese remainder theorem and just saying that taking products here, taking products in this world and taking products in this world are the same. Okay, so therefore, if h has this representation, then this must basically have the representation which is alpha 1 par q par k minus. Exactly. Okay, alpha r par q par k minus 1 by 2. Okay, so what do I expect to happen? If it so happens that one of these alphas were already 0 to begin with, then taking that corresponding power will continue to keep it 0. So nothing changes there. Okay, so let's just ask ourselves maybe before that, when will we get super lucky? When will that part itself succeed? Okay, so for now, let's just skip this part and let's just ask. So if it is the case that the GCD is non-trivial, it must mean that some GIs divide it and some other GJs don't divide it, which is the same thing as saying some of these alphas happen to be 0, some of them happen to be non-zero. In which case I would have returned G and like, okay, great, I've already found a GCD. So we might as well assume without loss of generality that I ended up picking a random H such that all of these alpha i's turned out to be non-zero. Okay, and now my clipboard thing is gone. So therefore, h bar q bar k minus 1 by 2, this is going to look like alpha 1 bar q bar k minus 1 by 2 all the way till alpha r bar q bar k minus 1 by 2. Okay, now let's ask ourselves, what are the chances that okay, that is I'm fixing an I, that for fixed I, we have that alpha per q per k minus 1 by 2. This is equal to plus 1. I mean, we just argued that roughly half of them satisfy that this is plus 1, and the other half satisfies that it is minus 1. Okay, so this is like it's about a half. The reason it's about a half is because of the 0 case that we got rid of. That we are assuming that all the alphas are not 0, etc., etc. So which is right, but it's about half. Okay, and similarly, you can ask, what are the chances that alpha per q per k minus 1 by 2 equals minus 1? This is also about a half. Which means what should happen is that in this particular polynomial, half of the coordinates are expected to be plus 1, half of the coordinates are expected to be minus 1. Okay, is that clear so far? I mean, so in fact, with at least a probability of half, one of them will be plus 1 and one of them will be minus 1, because the chance that all of them are equal to plus 1 is something like 1 by 2 power r. And the chance that all of them are minus 1 is also another 1 by 2 power r. So the remaining probability is at least a half if you do the right calculation. Okay, so therefore, with probability at least a half, some alpha I per q per k minus 1 by 2 is equal to plus 1, and some alpha I per q per k minus 1 by 2 is equal to minus 1. Okay, so therefore, with probability at least a half, okay, if I consider the polynomial h tilde plus 1, which is basically h per q per k minus 1 by 2 plus 1, what would happen? All the coordinates that used to be minus 1, I am now adding a plus 1 there, therefore they will all become 0. And all the coordinates that used to be plus 1, I am adding one more plus 1, so they will become 2. But fortunately, 2 is not 0 because q is an odd prime. I mean, it's not a prime, but q is odd number, so therefore 2 is not 0. So this basically means we'll have some coordinate equal to 0 and some coordinate equal to 2, which is not equal to 0. Okay, and that basically tells you that therefore probability that GCD of h tilde plus 1 with f is not equal to 1 is at least a half as clear. Okay, is this clear so far? So this is the, I mean, it's a beautiful algorithm in the sense that we are using everything on the right hand side is just in our mind. We don't really have access to it. At this point, all I was told is that some alphas, I mean, like, the alphas were chosen at random. If I chose h at random, that's the same thing as saying these alphas are chosen at random. Now, some of them could be 0, some of them could be non-zero, some of them could be like all sorts of crazy elements. So I somehow want to make sure that I increase the chances of some of them being 0 and some of them being non-zero. So I perform this operation, which is raising power q per k minus 1 by 2. And now I'm guaranteed that each of the coordinates are only one of 3 possibilities. Either they are 0, or they are plus 1, or they are minus 1. And fortunately, plus 1 and minus 1 happen roughly with probability half. Okay, so in order to change that plus 1 minus 1 probability half to 0 non-zero with probability half, you just either add 1 or subtract 1. It doesn't matter. You just want to convert one of these things to 0. And what the algorithm did was it just added 1 to that expression. And so now you have the, with very good probability, that some coordinate must have been 0 and some coordinate must have been non-zero. So therefore, you will definitely find a GCD. And that's it. That's the algorithm. Currently, the success probability, or rather the error probability is half. And if you are not satisfied with an error of half, you just repeat this a few times so that you reduce the error exponentially.
I
Okay.
have a question.
Yeah, go ahead.
Might be stupid. I don't know actually. I'm not.
No, please go ahead. Yeah.
Can you de-randomize it?
At the moment, we don't know how to do this, primarily because I don't know how to find an explicit point in which I know for a fact that one coordinate is 0 and the rest are non-zero in some sense. I mean, somehow it feels, sorry.
If we just consider the matrix, or written out the elements and consider the matrix for which 1 power q to the power k, q to the power 2k, like that, k square and k cube, like that, and another.
No, sorry. Can you go over it a bit slowly? I didn't follow.
If we consider the matrix that gives us the where it will be 0, -1 and 1.
So what do you mean by consider the matrix?
So in the proof that you are talking about, that the number theoretic case, I think we had done a matrix that is one sided is q to the power k, q to the power 2k, q to the power 3k, up to q to the power k square and k cube, so on. And
sorry, I still don't follow. What do you mean by one side and the other side? So what is the operation?
The row and column. The row and column.
Okay.
So you are saying here that we will get one for some case, right?
So by the way, this is not a linear map at all. I mean, in some sense, I mean, starting from h, the h power k is not a linear operation. So I don't know what precisely you mean by that.
Okay.
So it doesn't quite work out as nicely, and yeah, and in fact, but I mean, I'm hoping that some of you have seen the Miller-Rabin primality test. There is something very similar that you do there. You will try to basically say that you find some integer m with a certain property, and then you add 1 and then take the GCD and see if it is non-trivial or something. Except for for a different reason, that particular algorithm, there may be chances when it tells you what the GCD is, but there may be several other situations where it will just tell you your number is not prime, but it actually won't reveal you much information about what the GCD is or what the factor is or something. So anyway, we'll see the primality test, the deterministic primality test at a later point. That time maybe I'll mention a few more. Okay, so that's it. This is the Cantor-Zassenhaus algorithm, and I just want to mention a few things. So about what did we really use about this x power q power k minus 1 by 2 sort of stuff. The main property about this is that it's one of these algebraic operations that take an arbitrary non-zero element in your field to 1 or -1 with probability half roughly. It's just some such map that does this. Now the point is, if q is even, you can work with a slightly different map. I mean, x power q minus 1 by 2 doesn't make sense, because if q is even, then what is this even? I don't know what that is. So you need to come up with a different map. Turns out that here is a map, which I'll just leave it as an exercise. It's a very important function actually, but we won't need it for this course, so I'm not going to go too much into it. There's something called the trace map. So if q equals 2 power L, and if you define this bizarre expression that I have written down, okay, turns out this map will either be equal to 1 or it will be equal to 0. And both of these cases happens with probability half. Okay, and the proof of this actually follows from the two exercises I have written below. In fact, part A follows from part B. So part B basically says anything that I substitute from F2 to the L, the right hand side is 0. So which basically means either trace of x must be equal to 0 or trace of x plus 1 must be equal to 0. Which means the image is always either 0 or 1. And in fact, just by counting the degrees, etc., it will tell you half of them map to 0 and half of them map to 1. Okay. And you can think about why this map is called trace. I mean, clearly there must be something that you're taking a trace of. And yeah, there's a good reason for it to be called trace. Okay. So since I'm sort of out of time. So let me just briefly tell you at least the statement of the Chinese remainder theorem, which is something that we just assumed for granted. And we just told ourselves that some version of this ought to work and we work based on that. So that's something that I need to justify. So I'll do the full proof in the next lecture, but let me just give you the statement of the theorem, which is something that should seem familiar. Again, the throwing in words here like coprime, which seem unclear. But this is a general statement that you can make, that whenever you have R modulo a product of ideals, I need to define what the product of ideals mean. Turns out it is isomorphic to these sort of sub-quotients, R mod I1, R mod I2, turn out to R mod IK, as long as these ideals turn out to be coprime. And I'm just stating it in this way because this should look very familiar to what you are used to over integers. Because over integers, you will basically have said, if I'm looking at a residue modulo a number n, and this n splits as a product of pairwise coprime factors, then I can reduce modulo n in terms of modulo each of those coprime factors. So it's exactly along the same lines, and we will see that the proof of the Chinese remainder theorem that you're used to, once you set it up in the right language, it just follows for ideals in general. And what we used is a specific instantiation of these things, where these ideals were those irreducible polynomials. And they will satisfy this notion of coprime. Okay, so let me stop here. So just want to mention, so I would like to cancel this Thursday's class for some personal reasons. We'll meet again the next Tuesday, so 1 week from now. And just a reminder again that problem set 2 is out. As we'll have in almost all problem sets, there is a sage part and there is a non-sage part. And I'll again encourage you to, do anything that will sort of make you want to try out the problems. If that means you want to form groups, please do that. But of course, there is a general policy that, you have to write your own answers and mention the names of all collaborators, etc. that you have. And yeah, and I'm hoping that the problem set is insightful, because some of the questions there are quite, something that surprised me a lot. I learned a lot while teaching some of the things, so I put some of those in the problem set. And I'm hoping that you. Okay, so if there are any questions and so on, since we're already out of time, maybe we can take a couple of quick questions if there are any. Otherwise, we'll take it on Academy.
Thank you, sir.
Yeah. Okay. Great. So if so, let's just I'll put up the notes today on the Dropbox. Okay. Cool. See you next Tuesday, not day after.